are going to do something which might be familiar to many of you, but still we have to do it. So today we are going to do, we start doing a bit of dynamic programming. So have you seen this in Haskell?
Yes, sir.
Oh, you've seen dynamic programming also. Okay, good. So in any case, so let's revise it quickly. So so you know the Fibonacci sequence which we have seen in this course is Fn is equal to Fn minus 1 plus Fn minus 2, and Fn is equal to, let's say, 1, and F0 is equal to 0. You can define it, yeah, correct? So this uniquely defines a sequence, correct? So what is the sequence? Let me write F0 equal to 0 and F1 equal to 1. So now F2 is equal to 1, F3 is equal to 2, F4 is equal to 3, F5 is equal to 5, and so on, correct? Now, how would you write a program to compute the Fibonacci sequence? Simplest way to do that would be to write a recursive program, def fib n return fib. So first the base cases. If n is less than equal to 0, less than equal to 1, or just let's write it explicitly. If n equal to 0, then return 0, else if n equal to 1, return 1, else return fib n minus 2 plus fib n minus 1, correct? Now, what is the complexity of this function? Tell me. How much time would it take to compute the function, and how much time does a computation by hand take? Tell me.
Exponential time.
Exponential time. Why is it exponential time? Because if you write the recursion, it will be exactly this. Tn is equal to Tn minus 1 plus Tn minus 2. So if n is greater than equal to 2, correct? If n is greater than equal to 2 is equal to 1 otherwise, correct? So basically this is Tn is something like Fn plus 1 or some such, correct? So this is exponential time. So how do we reduce the time? Notice when we did this computation by hand, once we computed a number like F4 or F5, we did not recompute it again. So when we compute F6, if we do it by directly, then this would lead to an F5, that would lead to an F4, so this would lead to F5 and F4, which would lead to an F3 and F4. So F4 would be computed multiple times. This we avoid. And so how would we do this in practice? So we put so we use a technique called memoization. That is, any intermediate results that we compute, we store, correct? So how do we do this? So def fib memo in. So firstly, you would create a table in which you would store so table is equal to empty. Let's do it in a list, correct? Fib memo n, if table dot len, so table is equal to 0, 1, let's say. So if table dot len is less than n plus 1, are you with me? Then what do we do? Then return table n, table n, correct? Else table n is equal to fib n minus 2 plus fib memo. N minus 2 plus fib memo n minus 1. Return table n. Is this correct? Do people see what is happening? Will this work firstly? Maybe this will not work. So let's say t is equal to this. You calculated, now you know that, so table n is equal to t and return t. Correct? So compute, why did I do this? What is the difference between the two? Sorry, it should be outside. This should be outside. Sorry. So tell me, any objections with this?
So what is the purpose of the first if clause?
Huh? Sorry, I couldn't hear you.
So what is the purpose of the first if clause?
The first if clause, this one, this basically, if the table entry has already been computed, if fib memo n has already been computed, which is, greater than equal to, less than equal to, is greater than equal to n minus 1, n plus 1, then return table n. Now is it correct? So what I'm saying is, if the table n is defined, then return table n. When is table n defined? When the length of the table is at least n plus 1. Correct?
Yes, it's okay.
Otherwise, you compute the n minus 2th entry and the n minus 1th entry, add them, that is your t, and then table n is equal to set the table to t and return t. Correct? So I claim the complexity of this, assuming that all additions can be done in unit time, basically how many additions will there be? There will be only order, there will be some like n plus 1 additions or something like that, order n additions. It's not be.
Sir, what was the problem with the previous code?
Okay, the previous code said table n is equal to this quantity, correct? So,
Yes,
so at this time, so can somebody try it and tell me whether it works or not? the problem I think would be that Python would try to this left hand side. If it evaluates it after evaluating the right hand side, then it will be fine. But if it somehow checks for this, so just check. Can somebody try it out? Just write this table n is equal to fib memo n minus 2 plus fib memo n minus 1. Tell me. Okay, you try it out. Okay. Okay, moving on. We want to do this for other classes of problems. So, for example, one very well-known problem is counting path in a two-dimensional grid. Suppose all the vertical edges and all the horizontal edges are present from 0, 0 to m comma n, correct? Now, you want to compute the number of paths from 0, 0 to m comma n. What is the number of paths? Tell me. Tell me.
M plus n, choose m.
M plus n, choose m, correct? Or n,
Fine.
which is the same, correct? Is it m plus n, choose n? Yes, correct? So, this is easy to compute. This you have learned in discrete math. But now, suppose I start blocking some intersection. So this intersection is blocked, meaning no path can pass. And this, so then how do you compute the number of paths? Suppose one intersection is blocked at I comma j. Then now, what is the number of paths from 0, 0 to mn?
So we can compute the number of paths which pass through I comma j, which
Correct.
is the number of paths from 0, 0 to I comma j, and then the number of paths from I comma j to m comma n, and then subtract this from the total number.
Correct? That's what you're saying. Huh?
Oh, yes, sir.
Okay. Now, if I remove another point, then what is the number of paths?
The
I think
principal of
we can subtract. Yes, sir.
Tell me. Tell me.
Well, in this case, we can just subtract, but we'll have to use inclusion exclusion.
You would have to use inclusion exclusion. Very good. So inclusion exclusion. And what is the complexity of? So suppose you want to remove. So what would inclusion exclusion do? You would remove the paths that go through both. So I've drawn it like this, but I could have drawn it like this. So there'll be paths that goes through both the points and so on. Correct? And we would subtract out the things that go through one of the points and add back the things that go through both the points and so on. Correct? So if you have k terms, if you want to find the path in which k vertices are excluded, then how many terms do you have to add up? Tell me.
Exponential.
Exponential in?
The number of points excluded.
Yeah. So inclusion exclusion would say you would have to add up some 2 to the k many terms, correct? Something like that. Is that correct?
I think so, sir.
Okay. Now, can you give me an algorithm that is not exponential in k? That is polynomial in the number of points?
Sir, by adding terms, you mean both the number of terms being subtracted and added?
Yes, yes, that's what I meant.
Oh, okay.
So the number of terms will grow to be 2 to the k. And each term, I am assuming, even if it can be computed in order 1 time, which is not true, but even if that could be done, this would take 2 to the k time, correct?
Yes, sir.
At least. So now we want something which is polynomial in the number of excluded points. In fact, we want something which is polynomial in m and n. Then how would you do it? I mean, here the number of points could be as large as, this could be as large as 2 to the mn, correct? These are the total number of points. Total number of points in the grid. You can remove some large fraction of it, half the points you remove, and then your algorithm will run in 2 to the order mn time. You want an algorithm that runs in mn time. How will you do that? So there is a very simple way to do it, which is, so at a vertex, let's take a vertex so that both its neighbors were not blocked. Correct? Both its incoming neighbors were not blocked. Then what is the number of paths that are so I've drawn it here. Let me draw some of that. So this is ij. This is I minus. This is I comma j minus 1, and this is I minus 1 comma j. Correct? So now, if you knew the number of paths from 0, 0 to I minus 1 comma j, and number of paths from 0, 0 to I comma j minus 1, then how do you find the number of paths from 0, 0 to I comma j?
There are some.
So nij is equal to n I minus 1 comma j plus ni comma j minus 1. Assuming both I minus 1 comma j comma I comma j minus 1 are not blocked. That's correct now? And if suppose we are here, this is I minus 1 comma j, and now where is I? Which one is I? That is a good question. So which one am I taking to be I? This one. Okay. So I comma j. So this is blocked. Correct? This path, there cannot be a path from this. So what is the number of paths to ij? And this is not blocked. So then you would just write ni comma j minus 1 if only I comma j, I minus 1 comma j is blocked. Is equal to n zero if both are blocked, and these are the non-base cases. Correct? Now, what are the base cases? Is equal to 1 if and j equal to 0. So is this recursion correct? Does it count the numbers from 0, 0 to ij, assuming that some of these things are blocked? Tell me. Are you with me?
Yes, sir.
So this is clear, na?
Yes, sir.
Okay. And now how would you compute it efficiently? So this would seem like an exponential time algorithm, just as the Fibonacci was exponential time. But now you can use memoization, correct? So you build a table, and in the table you store the previous values. You first store the block values. So you put so how would you do it? For I is equal to 1 to n, for j is equal to 1 to n. If so firstly t I j equal to -1, and what else? T equal to 0 to m, 0 to j equal to 0 to m -1, let's say we'll label it. So whichever, yeah. So t0, 0 is equal to 1, and for I is equal to 0 to m -1. For we should say so okay, I will not write the routine. It is routine. So it's simple, correct? I mean, using the same memoization idea, you can write this function, correct? You just have to check. So you just have to encode this in the function, correct? What I have written here, correct?
So we could also construct a graph out of this and try
That's
to
very
solve
good.
it.
Yes, you could. So what you will be solving is some sort of number of paths between 0, 0 and so Nij would be the number of paths from 0, 0 to ij, correct?
Yes.
And you could give a graph theoretic explanation of that. Also, you have a DAG. You want to count the number of paths. If you do it in the topologically sorted order, consider the vertices in topologically sorted order, then all the predecessors, immediate predecessors results are available when you reach a vertex. And then you can just sum up the values of the immediate predecessors and get the value, correct? That's what you are saying, correct?
Yes, sir.
Yeah. And in this grid, this topological sort is very simple. So what is the topological sort? Can you tell me a topological sort? So one topological sort is this, meaning first this vertex, then this vertex, then this vertex, then this vertex, then this vertex, this vertex, this vertex, and so on, correct? Do you agree?
Yes, sir. We could also do row wise, I think.
We could also do a row-wise thing. That's very good. So first we do this, then this, then this, then this, then this. This is slightly simpler. Also, you could do a column-wise thing. You could go like this, correct? So any topological sort will work. These are three natural topological sorts that we know are there, correct? Okay, so having said that, we move on to something related but slightly different. So, so firstly, are there questions here? Tell me. Questions? No questions. Everything is crystal clear. So tell me, what is the complexity of counting or doing this count? How many operations, how many additions do you have to do?
So I plus j.
I plus j. What is I plus j?
If you want to compute nij.
Okay, why is that so? So for example, if you want to compute the value here, if you want to compute a value in the third row, how many things would you have done? 3 plus n, 3 plus m, or 3n. I guess what you mean is it is I times j, correct? So Tij Ti comma j is equal to I times j, or order I times j. How do you prove this? Tell me.
So we have two for loops, right? One from
We
0
have
to
two
I.
for. Yes, yes, yes.
And the other
We
from
don't
0
have, I have
to
not
j.
written it, but yeah, we have two for loops, so it is mn, correct? Another way to see it is that the number of additions, there is one addition per entry ij, correct? For every coordinate point, you are doing at most one addition. You're spending order one addition and miscellaneous other time. So in order one time, assuming additions can be done in order one time, each coordinate point can be processed in order one time. Since the number of coordinate points less than ij are I times j, we can do this in order I times j. Actually, that is not accurate. So we should say it depends on, depends on
So,
how
but
you are
we
doing it.
also check whether the adjacent points are blocked or not, right?
Yes, that is order one time, huh?
Yes, sir.
Because you're given a blocked array, an array which says blocked ij as input, correct?
Yes.
And probing that takes order one time. So Tmn is order m times n, correct? If you now, if you do it in diagonal order, then you would take Tij is equal, Ti comma j is equal to I comma j. Otherwise, you would take, if you do it in row measure order, then you would get order I times n, and or one in one you would get I times n, in the other you would get order m times j. Correct? If you're picking row by row, you would take this time, correct? Because completing one, if you do it in column order, then you would complete one column, that would take order n time, and therefore, no, what am I saying? There are, I rows, each is of length, sorry, so I into M. No, what am I saying? J into M, or I M into I, sorry. So if there are J columns, J rows, so it's all mixed up because our columns are in along I, that is the X coordinate and that is the Y coordinate, so they got mixed somehow. So this is the thing, correct? So do you understand? Correct. Okay. So now the next problem that we are going to see is the longest common word in two strings. So a string is so what is a string? A string is A till Z to the N, correct? So your two strings S1 comma S2, they belong to this thing, correct? So yeah. So if you have S1 and S2, this thing, you want to find the longest common word. So what is an example of this? For example, you say the word concoct and decoction. These are two different words, and this is a subword which is common between the two. And you can see that this is the longest subword, contiguous subword. Between the two. Common, contiguous sequence is this. Correct? So how would you find this? Tell me. So let's write this in. So what I want to show is that this is very similar to the previous problem, or it is somewhat similar to the previous problem. So we allow so what we want to do is to find a longest common subsequence, correct? So if we put a 1 where in there is a common letter between the two, so where would we put a 1? There's a 1 here, there's a 1 here, there's a 1 here, and there is a 1 here, there is a 1 here, and so on, correct? and this is a 1, and so on. Yeah. So now, how would we find this? Tell me. Am I missing something here? Yeah, I think. So you can see that the longest by inspection, this is the longest common word, correct? Basically, you have, you want to find a diagonal which consists of ones, which is the longest, correct? So now how do you do that? So firstly, let's say, one second, erase this. Correct. So I will put so everything which is blank is so this till here. So I will left one extra space. These are all zeros. And everything else that is blank is also zeros, correct? So now how do we organize the search? Tell me. So what is the longest word that ends at T here and N here? It is of length 0. Correct? Because N and T are different, correct? Similarly, this is 0, this is 0, and this is just doing the reachability in the number of the paths in the reverse, correct? So 0 is this 0 plus this 0. And now once you get a 1, you see that the the path that starts at so the path that starts at this T and at this T is common, correct? So the longest common word is of length 1, correct? So I should not have drawn this. So now this, so this is 1. Sorry. So this is our base matrix. Now we will, so this is like the ones are where paths are allowed to go and the zeros are where they are blocked. And you are looking for diagonals. So if I draw this with a different color, this would be the path that ends at T in both these is of length 1. The path that ends at T and C, this is again 0. This is again this 2. This is 3. This is 4. Correct? Are you with me?
Can you repeat the last part?
So what I'm saying is the you want to see what is the longest path that the longest word that starts at this position versus, say, let's say this position. That is of length 0, correct? This 0. Because the letters do not match.
Yes, sir.
Yeah. Do not draw this first 0. Yeah. So do you agree?
Yes, sir.
On the other hand, this C matches with this C. So there is a path of certain length, and that is one more than the value here, which is one more than the value here, which is one more than the value here. So working backwards, you first fill, suppose you fill the tables column wise. So so N, does it match with T? No. So you get a 0 here. Does O match with T? No, you get a 0, you get a 0. T, does it match with T? Yes. So you get a 1, correct? This, remember, is 0. These are 0. So 0, this 0 plus 1 is this 1. This is again 0, and there is no other T, correct? So these are all zeros, correct? Now you come here, you see N matches with C, so 0, 0, O matches with C, 0, I matches with C, 0. And these are all zeros in this. Unfilled were zeros. Now you see that C matches with C, so there is a 1 here. And now, therefore, this extends this by 1. So you get 2. So basically, what I'm saying is that Tij is equal to Ti plus 1 comma j plus 1 if whatever this array Aij is equal to 1 and is 0 otherwise. Ti plus 1 plus 1. Correct? Do you agree with me?
Yes, sir.
So, here I said 0. This would, so another way to so then the largest thing that occurs in the table is your answer, correct? But another way to interpret it is that if this is 4, then yeah, so that is correct. So this Tij gives the longest path. So what is the interpretation of Tij? Tij is the longest common word that starts at letter I of word S1 and letter J of S2, correct? And this is the simple recursion, and again you can fill it up by dynamic programming, correct? By memoization. Now, is this clear? Or are there questions? Tell me.
So if you find the maximum element of the matrix, which is
Sorry,
constituted,
I can't hear you. Sorry, can you please
so
speak
to
up a bit?
find the maximum element in the matrix, we
Yes.
just go through the whole thing again.
You can store the maximum that you have found. You can store the pointer to the maximum you have found till now. Correct? As you fill the table, you can maintain the pointer to the maximum length that you have found. Correct? So when you found this one, this was the maximum. Then this became the maximum. Then this became the maximum. Then this became the maximum. And these ones will not count because they are smaller than the maximum. And so on. Correct? Are you with me?
Yes.
Okay. Now I modify the problem slightly. I'll modify the problem slightly and try to find the longest common subsequence of two strings. So what is the difference between longest common subsequent and longest common word? A subsequence needn't be contiguous. A subsequence of a string is not necessarily contiguous. Correct?
Sir, one question. What is
Tell
the
me.
time complexity of the previous algorithm?
The time complexity of previous algorithm, you tell me. So how many entries are there in the table?
MN.
Mn, correct?
Yeah.
And what is the complexity of filling one entry of the table? Oh. Order 1, correct? If you knew ti plus 1 comma j plus 1, then you would fill it in order 1 time, correct?
Yes, sir.
So the total time taken is order mn. So it's a good question. Why? Because naively, if you were to do it, then how would you do it? How much time would it take? Suppose m is equal to n. How much time would this algorithm take? Not this algorithm, the naive algorithm. You would guess the value of I and j. You try out all possible ij such that I belongs to m and j belongs to n. So there are mn choices, and in each one of them you compute the longest word, which can be of length order n. Correct? So it would take order n time to do that. So mn into n is equal to mn squared, which correct? So if m is equal to n, this would take order n cubed time. While here we are taking n squared time. So we have shaved off a factor of n. Do you agree with me?
Yes, sir. Yeah.
And this algo is this equal to order n squared if m is equal to n. So we have shaved off a linear factor. Correct? Okay, good. So now longest common subsequence of two strings. So a subsequence of strings is not necessarily contiguous, correct? So what could be examples of this? Let's just take an arbitrary A, B, C, D, A, B, B, A, B, C, A, B, B, A. This and some other thing, A, B, D, C, B, A, C, D, A. So what is a common subsequence? This is one common subsequence. I'm not claiming that this is the longest, but because I've not done the calculation, but this is a common subsequence, correct? Which does not consist of contiguous this thing. So basically A, B, D, B, A, B, A is present in both the strings. And conceivably this is the longest, maybe there is a longer one, I don't know, correct? So how would you find that out? So now what would you do differently?
Replace the 0 by Tij, Ti plus 1, J plus 1.
So Tij is equal to, yeah, tell me.
Ti, if 1, then 1 plus Ti plus
Is equal to
1.
1 plus Tij if
1 plus Ti plus 1, J plus 1. If Aij is equal to 1.
Aij equal to 1, if Aij
Else, else equal to max J plus 1.
correct. Why is this so? This is what you were saying, correct?
It will be Ti plus 1, J plus 1. 1 plus.
Oh, sorry. Yes. Sorry. Yes, of course. Now is it what you were saying?
I was saying like replace 0 by Ti plus 1, J plus 1 in the above. Yeah, X is instead of max, but don't know if it's correct.
0 by Tij.
Like there was 0 if Aij is equal to 0.
If Ij equal to 0, yes.
Now if I replace 0 by Ti plus 1, J plus 1.
0 plus 1, J plus 1.
No, 0 instead of max this I was telling Ti plus 1, J plus 1, like, but not think that's correct.
No, see, so let's do this smaller string up till this point. Let's do this string up till some small point, till this point. So A, B, C, D. And here we have ABDC. Let's say this. And again, we have the same invariant, that it is the longest, slightly variant invariant, that longest common subsequence. Sorry. Correct. So longest common. So if you do this, what is the longest common subsequence? So again we have these labeled by this is 0. This so I will not write the zeros. I will just write the this ones. So this is 1, and this is 1. This is 1. This is 1, and this is 1. Correct. So now now we start putting, and these are initialized to zeros. So now this will be 0. 1 plus ti plus 1 if, but this is 0, so it is maximum of this and this, which is 0. Now here we see that this is 1, so we get 1 plus 0, which is 1. Now this is yeah, it's so this is again so now this is an important point. So what is the longest common sequence? It starts at letter D here and at the letter B here. Tell me, just by inspection, what is the longest common subsequence between D and BDC?
1.
1. Why is it 1? So that is why we took the maximum of these two, correct? Maximum of these two. So you have 0 coming from here and 1 coming from here, correct? And now this is still 1. And if we go here, then what is it? This is still, so this is 1. This is now what? Tell me. Between DC and CD, what is the maximum? This thing is 1, correct again? So you don't take the third one. This one is not an option. I mean, in this case it is, but I mean, you don't add 1 to both of them, or you don't add both of them, correct? But here you have this one, so this becomes 2. And here you have 2 and 1, so this again becomes 2. And this becomes 3, and then this becomes, no, this becomes, no, this was 0. So this remains 2, and this becomes 3. Okay, so having said that, I left out some part in the last one, but let's do it here. How would you find this string? I mean, the last one, it was very easy because you look at the maximum value and the next so many things are, the diagonal elements are exactly the word that you want, correct? So if this is 4, then the 4 letters, the 4 words, 4 letter string starting from this C inclusive is common. But here, how do we do it? Tell me. So if you see that this 3 was increased, so you are looking at where this came from, correct? The path like this. Sorry, this is wrong. Correct? So this gives you this 1 to 2 gives you the increase. This is D. This letter is common, and then this. No, I made a mistake. Sorry. Sorry. What is the? This is 1. Let me erase these and draw it properly. So this remains 1 because there was a 0 here before, correct? And now here you again there's a 0, so it is 1. This one is a 1 and there's a 1 here, so this becomes 2. And this becomes a 3. So basically tracing back the path, this is the path, correct? Let's say it came from here and from here, correct? So the longest word, this C matches, this one matches, then this one matches, B matches, and then A matches. Do people see this? Tell me.
Yes, sir.
Okay, so you can trace back the path by checking when which rule triggers it. If this is triggered, then Aij, and that means Aij is 1, and you include Ij in the word. If this is the case, whichever is maximized, this one or both, you pick one of them arbitrarily, both, otherwise you pick the maximum one, and then you see which one matches that, and so on, correct? So am I making sense? I'm not getting any response, so I don't know what is happening.
Sir, like, will both cases happen?
Both cases can happen. For example, in this one, in this one, see, there's a 1 from here and there's a 1 from here. Both cases can happen. The maximum can be achieved at both the ends.
I mean, the two cases in which, like, when Ij is equal to 1 and Aij is equal to 1, we have the A's. Okay.
Sorry.
No, sir. No, sir. It's clear, sir.
Okay. More questions? Okay. So we did longest common sequence, longest common word, and we did memoization. I leave the following problem for you to think about, that of edit distance. So you're given two words, S1 and S2, and you want to find the smallest number of edits that will convert S1 to S2. So you want to convert S1 to S2, and edit operations are insert a letter in S1, delete a letter in S1 from S1, and match the same letters in S1 comma S2, correct? So you want to convert S1 to S2 by changing a letter in S1, either inserting or deleting, or by matching the same letters in S1 and S2, correct? So how will you do this? Okay, I'll let you think about it. It's very similar to this longest common subsequence. One thing which I did not say is that this causes insert a letter alpha in S1. This has some weight W alpha. Delete a letter beta from W beta, and this is cos 0. So it's a weighted version of the previous. Okay, I'll let you think about it. I think there is very little interest in today's lecture. So yeah. Any questions? If not, then we conclude today's lecture with this. We meet again on Thursday. Okay? Thanks.
Thank you.
The binomial heaps, in particular, are amortization. So,
Okay.
what my understanding is that by analyzing it using amortized analysis, what we do is we essentially sort of mark everything in such a way that we assign zero cost to any linking operation.
Yes. So we have paid for a linking earlier, correct?
Yes, sir. So in particular, my question is, I'm not fully able to see why for an eager heap, melding is still log n, in the sense that rather so my understanding is when you want to meld, we check in every I guess digit slot whether we have the binary trees or not. If so, we link.
We will do the sum of the
deal with carries and so on. And in this
Yes.
case, since our linking is free, the log n complexity comes because we have to check every slot whether or not we have binary trees.
Yes.
Is that correct, sir?
So when you link two things, you pay for it by the thing that goes below's credit, correct?
Yes, sir. So, but given this, for insert, don't we still have to check log in many places? And so even though the linkings are all paid for, don't we still have to check isn't the cost still log in? This is the question. I wasn't able to see why this is not log in and this is order one. If we still have to check it.
No. With amortization, this thing. No, here there are carries also. No?
Yes, sir.
1 second. So, what is the question you are saying? Insertion is like adding 1.
Yes, sir. Sir, and all of our linkings, no matter whether or not there are carries or not, our linkings are paid for. So that doesn't contribute any time.
Yes.
But since we're using our meld function, however we define meld, since we're using that, shouldn't like suppose we're adding a 5-digit tree, to say it loosely, a 5-digit tree and a new tree that we just made with the
correct
with the insert thing. Shouldn't we still be checking 5 slots? So we're not checking. So yeah, that's my confusion.
So you are saying that when you add, so suppose this thing is 1, 1, 1, 1, 1, lots of ones, log in ones, and you insert 1, then the carry will propagate. Is that what you're saying?
Not exactly, sir. My question is, we still have to check for a carry, and that costs time. So irrespective of whether or not there's a carry, so no matter what number we have as a larger number, the one that we're inserting into,
yes, but
we still need to check every slot.
No, you don't, because if you do it sequentially,
oh yes, sir.
The moment you find that there is no carry, you stop. Do you agree?
Sorry, I couldn't. Oh yes, sir.
You stop, correct? So, and the carries that have happened thus far are paid for. Suppose there are 10 bits, correct?
Oh yes, sir.
5 of them, the trailing 5 are ones.
Okay, sir.
Then there is a 0. Correct?
Okay.
Now you add a 1, you add 1 node, you insert a node, correct?
Yes, sir.
So the first one adds with the first one and you get a carry. This is paid for by the bit you have there, correct? By the
Yes,
credit
sir.
you have in one of the two ones.
Yes, sir.
Correct?
Yes, sir.
And in the second one, it's again paid for by the credit that is there in this one. And so on till you reach the fifth bit, at which place there is again a carry, but at the sixth place, there is no carry. So
Yes,
then
sir.
you don't have to continue checking. So maybe there is an over this thing of one, this thing only, correct?
Sir, I get how it should be order one, sir, but my confusion is if it
Tell me.
I'm not able to reconcile this with meld being login, sir, because suppose we okay, so do we do it like this, sir? Do we, in our implementation of meld, do we, when we're adding, do we deal with all carries at once and then continue, or are we? Because I guess my confusion is, if we have our 5-digit, our 5 bits at the top and our 1 bit at the bottom, if we just add the 1 bit, deal with all the carries, and then realize that we don't have to do anything else, then this is ordered one time.
You are saying that if there are 5 bits there, and in the other thing, there are also 5 bits, correct? So you're adding 5 bits with 5 bits. You add 1 to 1, you get 1 0. 1 goes here, then you add 2 of them, and 1 goes here. So I see your problem. So your point is that anyway, for both of them, it's paid by this thing, correct? Paid
yes, sir.
for by the
Yeah.
credit.
And I was able to reconcile it for meld being login by saying that we must have implemented it in such a way that we have to check all of the bits to even check if there's a carry, in which case the linking is free, but that checking we have to do login times. But this doesn't match up with insert. And
yeah. So yeah. So in meld, even if there is no carry, you have to do the checking. But
yes,
here,
sir.
because the numbers could be something like 1 0 0 0 0 1 and something else. I mean 1 1 1 1 1 1. So there are lots of zeros in one in the first this thing, and there are lots of ones in the second one. Correct?
Yes, sir. Yes, sir.
Or let's say there are the second one is also sorry. So even if there is no carry in the meld, you still have to go through all the bits.
Yes, sir.
But in insert, you don't have to go through all the bits. You only have to go up to the point that there is a carry.
Yes, sir. But we implemented insert with meld, right? So should we?
Yes, but that meld then takes order one time. That particular instance of meld as a black box, I guess it is the same thing.
Okay. Right. So yeah. Okay. But okay.
So you are saying that we should implement it separately? Yes. So maybe what the mistake I was making was that this greedy insert, you don't do it via meld.
Okay.
Only the lazy insert you do via meld.
Okay. So I think I get it now, sir. Yeah.
Okay. Thanks for the clarification. Yeah.
Thanks a lot, sir.
Yeah. Thanks.
Thank you, sir.
Thanks.
Excuse me, sir.
Yeah, tell me.
So what's the syllabus for the quiz?
Syllabus for the quiz, that's a very good question. If it's next week, then it is till today. Otherwise, it's till next next Thursday. Till Thursday, correct? So I doubt I will be able to have a quiz on Thursday because there's a paper deadline I'm chasing, and I'll be busy till Thursday. So in all probability, the quiz will be next Thursday, so you don't have to worry about it right now. Okay?
Okay, sir. Okay, sir.
Okay.
Thank you, sir.
Thanks. Bye.
Thanks a lot, sir.
Thank you. Bye.
Thank you, sir.